Welcome to our deep dive into the fascinating world of rotational motion and systems of particles. In this chapter, we'll explore how objects behave when they rotate, how their mass is distributed, and why these concepts are crucial in both physics and engineering. Whether you're a student preparing for exams or just curious about the mechanics behind spinning objects, this video will guide you through the essential principles, derivations, and application. Let's begin our journey by understanding the very foundation, the center of mass and how it governs the motion of systems. Center of mass is a fundamental concept in physics. It's the specific point in a system of particles where the entire mass of the system can be considered to be concentrated for the purpose of analyzing motion. Imagine balancing a ruler on your finger. The spot where it balances perfectly is its center of mass. This point helps us predict how objects will move when forces act upon them, making it a cornerstone for understanding both linear and rotational dynamics. Let's derive the expression for the center of mass for a simple system, two particles. Suppose we have two masses m1 and m2 located at positions x1 and x2 along a straight line. The center of mass xcm is given by the formula, xcm equals m1 x1 plus m2 x2, m1 plus m2. This equation shows that the center of mass lies closer to the heavier mass. This principle extends to more complex systems, but the basic idea remains the same: mass and position together determine the center of mass. Torque is the rotational equivalent of force. It measures how much a force acting on an object causes that object to rotate. The magnitude of torque depends on the force applied, the distance from the axis of rotation, and the angle at which the force is applied. In everyday life, using a wrench to loosen a bolt is a perfect example of torque in action. The longer the wrench, the greater the torque you can apply with the same force. Now let's derive the relationship between torque and angular acceleration. According to Newton's second law for rotation, the net torque tau acting on a body is equal to the product of its moment of inertia I and its angular acceleration alpha. Tau equals E alpha. This equation is fundamental in rotational dynamics, just as F equals ma is in linear motion. It tells us that the greater the moment of inertia, the harder it is to change the rotational speed of an object. Angular momentum is a measure of the amount of rotation an object has, taking into account its mass, shape, and speed of rotation. It's a vector quantity, meaning it has both magnitude and direction. In mathematical terms, angular momentum L is the product of moment of inertia I and angular velocity omega. L equals omega. This concept is crucial for understanding how spinning objects behave, from figure skaters to planets. Law of conservation of angular momentum states that if no external torque acts on a system, its total angular momentum remains constant. This principle explains why a spinning ice skater spins faster when pulling in their arms. Mathematically, if the net external torque is zero, then the initial angular momentum equals the final angular momentum, L initial equals L final. This law is fundamental in physics and has wide-ranging applications, from atomic particles to galaxies. Linear momentum and angular momentum are related but distinct concepts. Linear momentum refers to the motion of an object moving in a straight line, while angular momentum deals with rotation around an axis. Linear momentum is given by P equals mv, where m is mass and v is velocity. Angular momentum, on the other hand, depends on how mass is distributed relative to the axis of rotation and is given by L equals E omega. Both are conserved in isolated systems, but they describe different types of motion. Moment of inertia is a property that quantifies how difficult it is to change the rotational motion of an object. It depends on the mass of the object and how that mass is distributed relative to the axis of rotation. The farther the mass is from the axis, the greater the moment of inertia. This concept is key to understanding why some objects spin easily while others resist rotation. Let's derive the moment of inertia for a uniform rod of mass m and length L about an axis passing through its center and perpendicular to its length. By integrating the mass elements along the rod, we find that the moment of inertia is I equals 1/12 ml2. This result shows that the distribution of mass relative to the axis greatly affects rotational resistance. For a thin ring of mass m and radius r, the moment of inertia about a diameter is I equals 1/2 Mr. 2. This is derived by considering the mass elements distributed along the circumference and their distances from the axis. The result highlights how geometry influences rotational properties. For a solid disk of mass m and radius r, the moment of inertia about its central axis is I equals 1/2 Mr. 2. This is calculated by integrating over the disk's area, considering each mass element's distance from the axis. This value is crucial for understanding the rotational behavior of wheels and disks. Parallel axis theorem allows us to calculate the moment of inertia of a body about any axis parallel to an axis through its center of mass. The theorem states I equals ACM plus M2, where ICM is the moment of inertia about the center of mass, M is the mass, and D is the distance between the axes. This theorem is especially useful in engineering and physics problems involving composite bodies. Perpendicular axis theorem applies to planar objects. It states that the moment of inertia about an axis perpendicular to the plane IZ is the sum of the moments of inertia about two perpendicular axes in the plane IX and IY. IZ equals IX plus IY. This theorem simplifies calculations for flat objects like disks and rings. Equilibrium in rigid bodies occurs when the body is either at rest or moving with constant velocity, and there is no net force or torque acting on it. In such a state, the body does not accelerate linearly or rotationally. Understanding equilibrium is essential for analyzing structures and machines, ensuring they remain stable under various forces. For a body to be in rotational equilibrium, the sum of all torques acting on it must be zero. This means that clockwise and counterclockwise torques balance each other out. Additionally, the sum of all forces must also be zero for complete equilibrium. These conditions are vital for designing stable structures and mechanisms. Rolling motion occurs when an object, such as a wheel or ball, moves along a surface while rotating about its own axis. This type of motion combines both translational and rotational movement. Rolling is common in everyday life, from vehicles on roads to balls in sports, and understanding it is key to analyzing real-world motion. Total kinetic energy of a rolling object is the sum of its translational and rotational kinetic energies. For a body of mass m, radius r, and velocity v, the total kinetic energy is k total equals 1/2mv2 plus 1/2 omega 2. This formula helps us understand how energy is distributed in rolling objects and is crucial for analyzing motion in vehicles and machinery. When a disc rolls on a horizontal surface without slipping, every point on the rim comes into contact with the surface momentarily at zero velocity. The center moves forward with velocity v, while the disc also rotates with angular velocity omega. This combination of motions is what makes rolling unique and efficient for transport. Precession is a fascinating phenomenon observed in spinning gyroscopes. When a torque is applied perpendicular to the axis of rotation, the axis itself begins to trace out a cone-shaped path. This motion, known as precession, is crucial in navigation systems and helps explain the stability of spinning objects like bicycle wheels. Rotational dynamics plays a vital role in engineering and technology. From designing engines and turbines to understanding the motion of satellites, the principles of rotational motion are applied everywhere. Mastery of these concepts leads to safer, more efficient machines and innovative solutions in various fields. Let's quickly recap what we've covered so far. We started with the center of mass, explored torque and angular momentum, and discussed the moment of inertia for various shapes. We also examined important theorems and the conditions for equilibrium. These foundational ideas set the stage for deeper exploration into rotational motion. Consider a playground seesaw with children of different weights sitting at various distances from the pivot. The seesaw balances when the torques produced by each child about the pivot are equal and opposite. This real-life scenario beautifully illustrates the concepts of torque, center of mass, and rotational equilibrium in action. Bicycle wheels are designed with rotational dynamics in mind. Their mass is distributed along the rim, increasing the moment of inertia and providing stability during motion. The conservation of angular momentum helps keep the bicycle upright, especially at higher speeds. Flywheels are used in engines to store rotational energy. Their large moment of inertia allows them to maintain a steady rotational speed, smoothing out fluctuations in power delivery. This application showcases the practical importance of understanding rotational motion in engineering. When a figure skater pulls in their arms during a spin, their moment of inertia decreases, causing their angular velocity to increase. This is a direct demonstration of the conservation of angular momentum and is a striking example of physics in sports. Satellites use rotational dynamics to maintain orientation in space. By adjusting their angular momentum with internal mechanisms, they can point instruments or solar panels in desired directions. This is crucial for communication, observation, and navigation. Car wheels are engineered to optimize rolling motion. Their design ensures efficient energy transfer from the engine to the road, minimizing losses due to friction and maximizing stability. Understanding rolling motion and moment of inertia is key to automotive innovation. In factories, rotating machinery such as turbines and gears rely on principles of rotational motion. Engineers must calculate moments of inertia and torques to ensure safe and efficient operation. This knowledge prevents mechanical failures and improves productivity. Opening a door is a simple example of torque in action. The farther from the hinge you push, the easier it is to open the door. This everyday experience demonstrates how torque depends on both force and distance from the axis of rotation. Planets rotate about their axes, exhibiting angular momentum on a massive scale. The conservation of angular momentum explains why planets maintain their rotation unless acted upon by external forces. This principle is fundamental in astrophysics. In physics labs, experiments with rotating platforms and weights help students visualize and measure concepts like moment of inertia and angular momentum. These hands-on activities reinforce theoretical understanding and build problem-solving skills. Spinning tops have fascinated people for centuries. Their stable rotation is a direct result of angular momentum and precession. Studying these toys provides insight into the fundamental laws of rotational motion. Calculating the moment of inertia for different shapes involves integrating mass elements at varying distances from the axis. This mathematical process is essential for engineers and physicists working with rotating systems, ensuring accurate predictions and designs. To sum up, rotational motion involves a rich set of concepts, from center of mass and torque to angular momentum and moment of inertia. Mastery of these ideas is not only crucial for academic success, but also for practical applications in technology, engineering, and daily life. Let's test your understanding with a quick quiz. What is the formula for the moment of inertia of a rod about its center? How does angular momentum differ from linear momentum? These questions help reinforce the key points covered in this chapter. Students often confuse torque with force or forget to account for the axis of rotation when calculating moment of inertia. Being mindful of these common mistakes can help you avoid errors and deepen your understanding of rotational dynamics. Gyroscopic stability is the reason spinning wheels and tops resist changes in orientation. This property is harnessed in navigation systems, such as those used in ships and aircraft, to maintain direction even in turbulent conditions. Robots often rely on precise rotational motion for tasks like picking, placing, and assembling parts. Understanding torque, angular acceleration, and moment of inertia is essential for designing efficient and accurate robotic systems. Medical devices such as centrifuges use rotational motion to separate substances based on density. The principles of angular velocity and moment of inertia are crucial for their operation, ensuring effective and safe results in laboratories. In rotational systems, energy conservation plays a key role. The total mechanical energy, including both translational and rotational components, remains constant in the absence of external forces. This principle is essential for analyzing the motion of wheels, gears, and other rotating objects. Nature is full of examples of rotational motion, from the spinning of hurricanes to the rotation of galaxies. These phenomena follow the same physical laws we study in the classroom, demonstrating the universal applicability of rotational dynamics. Emerging technologies such as advanced gyroscopes and energy storage systems are pushing the boundaries of what's possible with rotational motion. Continued research and innovation promise exciting developments in transportation, robotics, and beyond. To master rotational motion, focus on understanding the core concepts, practice solving problems, and relate the theory to real-world examples. Visualizing the motion in drawing diagrams can also help clarify complex ideas and improve retention. Rotational motion is a powerful and pervasive aspect of the physical world. From the smallest particles to the largest galaxies, understanding how objects rotate unlocks a deeper appreciation of nature and technology. Keep exploring, and you'll find rotational dynamics at the heart of countless phenomena.